This is a continuation of the chapter 3 video after my phone stopped in the middle of the last video. And I don't know how far along on this problem number 8 I was when it stopped, but let me do this instead. Since their problems are often really messy, let's just do another example so you'll understand it better, and then I can come back to that one. So what if I just have a simple data set like 1, 2, 5, 10, and let's say 22. 1, 2, 3, 4, 5. There's 5 numbers here, so that's called n. The sample size is 5. And if you want to do the range first, and range is a separate calculation, you take the maximum minus the minimum. That's 21. Once you answer that, if sometimes the problems only ask for, they might just say find the standard deviation only. But the ultimate goal is to find the range, the variance, and the standard deviation. Most problems ask for all 3 of those. And the range is a separate calculation. It's like you don't use the mean to find the mode. They're just separate calculations. So if I'm going to do variance second, variance is this 5-step process, and then in essence, standard deviation is the 5th step of the process. So step 1 of variance is to find the mean. And this is where you add them up and divide by how many there are. 1 plus 2 plus 5 plus 10 plus 22, and divide by 5. So 1 plus 2, 3, plus 5 is 8, plus 10 is 18, plus 22 is 40. 40 divided by 5 is 8. See, this isn't that bad of a process if the mean comes out well. The one I was doing at the end of the last video, the mean was 173.625, and I was actually rounding it off too. So that made all this really messy because of that. But if you get a nice answer like that, 8, then here step 2 becomes a lot easier. Take each number minus the mean. So the first number is 1. 1 minus 8 is negative 7. Then go to the second number, 2. 2 minus 8 is negative 6. The third number is 5. 5 minus 8 is negative 3. 10 minus 8 is 2. And 22 minus 8 is 14. Each number minus the mean. And as I said in the last video, if you add this column up, unless there's rounding issues, it should always add up to 0. In fact, that's a good double check to make sure that's true, because 2 plus 14, these two positive numbers, 2 plus 14 is 16. And then if you do the 3 negatives together, negative 7, negative 6, and negative 3, that's negative 16. There may be more of the positives or more of the negatives. Those don't have to balance, but all the negatives added together plus all the positives added together, they cancel out. So the negative 16 cancels the positive 16, and that always adds up to 0. This is why we even have step 3. Step 3 is to try to get rid of this issue where the negatives cancel the positives by making them all positive. So if you square every answer, they'll turn positive because anything squared is positive. Negative 7 times negative 7 is positive 49. Negative 6 times negative 6 is positive 36. Negative 3 times negative 3 is positive 9. 2 squared is 4, and turns out 14 squared is 196. And if you didn't know that, you could, any simple calculator could do that. 14 times 14, 196. So now if I add this column up, 196 plus 4 plus 9 plus 36 plus 49, it's not going to add up to 0. 294. So that's step 4, is to sum up the squares. the sum of this column is 294. Whoops. Starting to write the 9. 294. The fifth and last step of variance, it depends if you're doing population or sample variance. Usually we're doing sample variance, so you can always assume it's sample unless they say otherwise. So the variance is this sum that you just got. And then the strange thing is you would think to divide by 5 the way the mean was divided by 5, and you would if you were doing population variance. But sample variance, which is done much more often, you divide by 1 less than that. So in this case, 4. When I was doing this problem before the video ran out, the sum turned out to be this messy decimal right here. And I was dividing, there were 8 numbers in the original problem, I believe. 1, 2, 3, 4, 5, 6, 7, 8. So that's why maybe you can't see it, but there's a 7 here. I divided that by 7. It's always 1 less than how many numbers there were. So 294 divided by 4, if the problem asks for variance, which usually it does, but sometimes they know you have to do this anyway to get the standard deviation, so sometimes they don't ask for it. But you're going to have to get the variance even if they don't ask for it, 73.5. Then, in essence, the standard deviation is the sixth step of the process because it's the square root of the variance. It's its own answer usually, but it's really the sixth step of the process. So if I square root 73.5, it's 8.57, or wherever you want to round to, 8.57. Maybe they're going to make it 8.6. It just depends what they want me to round it to. I'll just say 8.6, since this one was 0.5, this can be 0.6. So this is the process of finding range, variance, standard deviation. Range is just its own calculation, and it's very easy. Most people get that right. Variance, there's nothing hard unless the numbers you're working with are messy. It's 5 steps. You got to remember the 5 steps, but you just find the mean. That's junior high work. Take each number minus the mean is extremely easy with a calculator. Square them all, add them up, and divide by 1 less than how many numbers are, and that's the answer to variance, 73.5 in this example. Then, in essence, the standard deviation is the 6th step of the process, and you square root the variance answer you got, and that's how I got 8.6. And here's another thing, too. Look at 8.6. 8.6 is pretty close to 7 and 6, and it's not too far away from 3, 2, and 14. It's really close to 7 and 6, though. In essence, what this 8.6 represents, it's kind of like an average of 7, 6, 3, 2, and 14, if you ignore the negatives on them. So it's saying each number, on average, is about 8.6 units away from the center of the data, where 73 is way too big. 73 is too big because when I square a single-digit number, it turns into a double-digit number. When I square a double-digit number, it turns into a triple-digit number. The process of squaring, just to make them positive, makes the numbers way too big, so that's why the variance is way too big. The variance doesn't represent what's happening here. But the opposite of a square is a square root. So the fact that we squared them in step 3, that's why, in essence, step 6 is the square root. That undoes the squaring, in essence. So then it brings the answer back to the level we should have been at if we didn't have this issue of this main column right here always adds up to 0 because the positive and negatives cancel each other out. So the problem I was trying to do, number 8, before my phone just suddenly cut off on its own, and I may have done the range first. Maybe the problem didn't ask for range. But yeah, we could have done range first. And then this is when I was doing variance. And I found the mean first, but it was a real messy decimal. Then I did each number minus the mean, and they were all messy decimals. Squared them all, more messy decimals, add all that up, and then I divided by 7. And it came out to 3878.0 if you round to the nearest tenth, 8.0, because it was actually 7.9, and then there was an 8 after that. And then the square root of that was 62.3. So go back here to the assignments. We've completed Chapter 1 homework and the quiz on Chapter 1. We've completed Chapter 2 homework and the quiz on Chapter 2. So we're currently working on Chapter 3 homework, and then there's going to be a quiz on Chapter 3 very soon. And then you can review for the test before taking the test. The test will have a 2-day window. And since all these things from the review on up, they're all due February 11th, 11:59 p.m., that's when the test is due. So that means you can take the test on February 10th or February 11th. And you get one attempt only, but one of those 2 days you should take the test. But hopefully you finish all the homework and the review before you take the test. And there isn't going to be a video for the review because it's just more similar problems from all the homework. So if you get stuck in any of the review problems, go back and watch one of the 3 chapter reviews, since there's no problem in the review that's different than any homework problem. But at least the review narrows down what you should focus on the most. The homework has some problems that we are learning, but they're just not going to be on the test. Okay, so Chapter 3 homework. I didn't know the phone stopped when I was working problem number 8. And then when I finished number 8, then I saw the phone had stopped. So I guess I was talking to myself for a while, but okay, so let's pull this number 8 up again. See how it did ask for the range first. Reason I didn't have it written down is it was just easy and I did it right here. So the highest number was 271 and the lowest number was 128. So if you do 271 minus 128, there's the 143 answer. Oh, I guess I found the wrong number. There's a smaller number, 106. So 271 minus 106, that's the 165 answer from that I did. I'm pretty sure that was part of the last video. And then now this is weird how they're putting standard deviation first and then variance. But you find the variance first, actually. So the variance was 3878.0. I actually got that correct. And then I square rooted it and got 62.3. They did want 1 decimal place. 62.3. Where do I have that? There, see, 62.3. And then when I was about to finish the problem, that's when I noticed that the phone had stopped recording. But I did have 3878.0 and 62.3. So really you should just do this all the way out. Do all 6 steps basically. Really technically the variance ends at the end of step 5. And usually in a homework problem they would ask you to fill that in first and then calculate the standard deviation. Here they wanted the standard deviation first just because it's used more often, I guess. But you got to answer all of them anyway. So just do the variance, then do the standard deviation, and then fill all 3 of these answers in if all 3 of them are here. And I guess it won't let me finish this, but how useful are the measures of variation for someone searching for a room? So usually what this comes down to is how large is the standard deviation? When standard deviations get like bigger than 10 or so, I mean, it's just a rough guideline, but around 10 or so, when standard deviation's more than 10, then you're starting to get a wide spread of your answers. And it's kind of logical here too. If these are how much it costs for 1 night in a hotel, the cheapest room was $106, but the most expensive was almost $300. That's a big difference right there. It's almost 3 times as large, 100 all the way up to 300. So that's a very wide range of answers. And that's what they're getting, how useful it is. Then it's not so useful so much. If you can get a low standard deviation like 2 point something, 7 point something, then that shows you that most of the numbers are close to each other. And then it could be useful to work with that. So I'm not sure what this answer should have been because it won't let me do it anymore, but it should definitely be one of the choices where it says the measure of variation are not very useful in this problem because, see, it's not this one. The values are nominal data. Nominal is when you just name and categorize things. These are definitely not nominal. We definitely have, this is ratio amounts because you can't charge negative amount of money for a hotel room. But you could get a free night at a hotel if you were some kind of rewards program, and after you stayed 10 nights, maybe they give you the 11th night for free. So it does start at 0. These are ratio type of data, not nominal. So the answer is definitely not B. Oh, I guess it will let me answer this. Okay. So it picked up where I left off because I just stopped the problem once the phone stopped. The measure of the variation are not very useful because when searching for a room, low prices, location, good accommodations. Yeah, see, that's another thing is not only is the standard deviation quite high, 62, but there's other factors too. People don't just go by price. Sometimes the location matters more, or what accommodations they have. Do they have a pool? Do they have a fitness center? Do they give breakfast? Do they have free parking? All of this can play a role in it too. So just the standard deviation alone wouldn't always tell you something. So there's number 8. And hopefully that extra problem that I did with the simpler numbers, that hopefully showed you how to do that a little bit better. Okay, I'm noticing we're still in 3.2 here. And let's see, when does 3.3 start? 2 more problems, and then there it is. Okay. So the video I previously made almost got you through section 3.2, but not quite. Okay, so here's I'm pretty sure I know what's going on here at the end of section 3.2. When they say it's bell-shaped, there's a distribution of blood counts that are bell-shaped. And they give you a mean in the paragraph, and they give you a standard deviation. So now you're working with both of these ideas. Okay, so let me open up a new board. Number 9. This is a concept at the end of section 3.2 called the empirical rule. The empirical rule, first of all, it only works if you have a bell-shaped or what's called a normal distribution. And we're going to learn more about the normal distribution in chapter 6, but this is kind of a short introduction to it. Bell-shaped. The problem clearly said bell-shaped. That's how I knew which kind of problem we're doing. So once you hear that, they should definitely tell you the mean and the standard deviation. This will always be given to you in an empirical rule problem. Now, again, they love to just do real messy numbers. They got 254.8, 254.8, and the standard deviation is this 60.8 over here. $60.8. These two have to be given to you to do this kind of problem. Then, as soon as I see that I'm doing an empirical rule problem, I don't even read the question yet. Make a number line. If you make a number line first of every possible answer, then it takes a little bit of the pressure off of trying to calculate things after you realize what they're asking you to do. Make a number line and put the mean in the middle. And I like to circle this one so I remember that's the starting point. Now, with the empirical rule, it turns out almost everybody lands within the first 3 places each way. You could go past that, but usually 3 is good enough. So I'm just going to mark 3 more spots, always 3, and take this mean and start adding the standard deviation to it. So take 254.8 and add 60.8. 315.6, that's right here. And then do it 2 more times. So add 60.8, 376.4, and 1 more time. Add 60.8 again. 437.2. Now go back to the mean, and we want to go 3 this way too. The mean's near the middle, and then we're extending out both ways. We got people that are above average, and we got people that are below average is what's going on here. So take 254.8, start over again. That's why I circled it so I knew where to go back. And now subtract 60.8. When you go to the left on a number line, you subtract. That's 194 exactly. 194. Subtract 60.8. 133.2. Subtract 60.8. 72.4. So these are what are called the raw scores. Whatever you're actually doing, if you're taking like a SAT test or you're doing some kind of measurement of some kind, like people's height or their IQ or things like that, those are called raw scores, what you would actually get in the experiment or whatever you're measuring. Then what we compare them to are called z-scores. Z-scores tell you how many places you are from the mean. So you're 0 away from the mean if you're at the mean. So if anybody got a score of 254.8, they would be 0 away from the mean. If you get 315.6, you're positive 1 spot away from the mean. 376 is positive 2, and 437 is positive 3. And then you also get negative 1, negative 2, and negative 3 for these other three numbers. Any kind of human measurement, height, weight, hat size, hand span, arm length, IQ scores, they all land on these symmetrical bell-shaped graphs. That's why it's called the normal distribution, is that it just normally happens in nature to do this. And it turns out there's three numbers to memorize. People that land within one place of the mean on either side, that occurs about 2/3 of the time, or 68% roughly. 68% land from here to there. They're negative one place all the way up to one place away from the mean. People that land within 2 standard deviations either way, that occurs 95% of the time. And 99.7% of people or objects or whatever you're doing will land within 3 standard deviations of the mean, as long as the graph's bell-shaped. So this is called the empirical rule, and at this point, the textbook just tells you memorize 68, 95, 99.7. That's 1, 2, and 3 places. So now I can go to the question. Approximately what percent of women have blood counts within, within 3 standard deviations? If it says within or between, then it's either 68, 95, or 99.7. Now, I guess I could have answered this without drawing a graph because they literally said within 3. Usually they don't mention that, and they'll just say, what percent of women are between 72.4 and 437.2. So here they were nice enough to tell you within 3. As soon as you hear 3, you know that's 99.7 if you have those 3 numbers memorized. But if it said between 72.4 and 437.2, if you drew a number line, then it's just a search for those 2 numbers on the number line. 72.4 is negative 3 places from the mean. 437.2 is positive 3. And in chapter 3, they're never going to give you different ones. You're never going to get negative 3 with positive 2. You'll need chapter 6 knowledge to do that. So it's either going to be negative 1 and 1, or negative 2 and 2, or negative 3 and 3. That's all you can do at this point. So if they say 1, 2, or 3, then you can know the answer is 68, 95, or 99.7. But if they say between, say they said between 194 and 315, then I would say it's 68, since that's one place away. If they said between 133 and 376, then I would say 95 for 2. Here they said between 72 and 437, then that's why it's 99.7. In case you get a problem where it just says between. That's called the empirical rule. See, this one didn't tell me how many standard deviations. See, they were trying to be easy on you with part A. Part B just says between the 2 numbers. So they didn't say if that's 1, 2, or 3 away. So then now if you drew the number line ahead of time, now you can just look these 2 numbers up. You don't have to like calculate in your head how many places are these. So find 133, find 376. They're either going to both be 1, or they'll both be 2, or they'll both be 3 away. Then probably not 3 because we did that one already. So are these 2 numbers, are they the ones that are 1 away, or are they 2 away? Let's see our number line, 133 and 376. Those 2 are both 2 away, apparently, because there's negative 2. And yep, 376 is positive 2. Since they're both 2 away, then I go to the second memorized percentage of 95. That's called the empirical rule. It gives you a rough estimate of how many people land in a certain range of values, but you're kind of limited in what you can do on this until you learn chapter 6, then we can do a lot more with it. Now, number 9, the nice thing about 9 was it said it was bell-shaped. See this bell-shaped right here? the empirical rule is the better rule because it's more accurate. But the downside is it only works if you know the shape of the graph is bell-shaped, which at this point they'd have to tell you that. So if they don't tell you the shape, or if they definitely tell you it's not bell-shaped, then you can't use the empirical rule. And there was a Russian guy named Chebyshev who came up with a more conservative rule. What happens if it's not bell-shaped, or what happens if you don't know the shape, or you know it's not bell-shaped? So it's done very similarly. The process is the same, it's just the percentages are different. And here they're being nice to me and they're telling me how many standard deviations. It says within 3. But if they said between this and that, then I could make my own number line and do that. So let me just make a chart here. Okay, so this is empirical rule. Empirical rule versus Chebyshev's. So one of two things always happens. They either say go between this and that, and then if you have a number line, you can figure out is it 1, 2, or 3, or 4 places. Or they'll say within 1, 2, 3, or 4, literally. So it's always 1, 2, 3, or 4. Chebyshev's actually goes to 4, where empirical really only goes to 3. So the 3 percentages for empirical rule are 68, 95, and 99.7. And we don't ever really go past that, so the fourth one doesn't matter. In Chebyshev's, it turns out the first one doesn't matter because it's so conservative. It says at least 0, and everything's at least 0. But the second one is only 75 rather than 95. See, it's more conservative, so it's a lower amount. And that way, if the graph is skewed left or right, highly skewed one way, then it covers that fact that it's unbalanced. The third place is 89, and the fourth one's 94. So even after 4 places, you're still not as far along as what empirical rule is after 3. So this number 10 homework problem, it told me it was 3 standard deviations, and it even said use Chebyshev's. So then I can know, okay, that answer is 89 instead of the usual 99.7 that we got in the previous problem. So it says use Chebyshev's. They told me that. And it said within 3, so I didn't have to make a number line to figure out how many spots out I am. But they could have given me the mean and standard deviation. I could have made a number line, and then they could have said go between this and that. And then I would have to count, are they both 1? Are they both 2? Are they both 3? Are they both 4? Then you could know which answer it would be. So since I'm 3 out, on Chebyshev's 3 places out is 89 instead of 99.7. So the point of this is, in case not every graph is bell-shaped. It's actually a special thing that bell-shaped and normal distributions, they happen a lot in nature, but in statistics, not every distribution is normal or bell-shaped. The minimum possible tablet count within 3 standard deviations. Okay, so this is what they're talking about here is, what are those 2 numbers on the number line? So here I'm not going to make a number line since I was able to answer part A already. But let's take this mean of 255.1. If I add the standard deviation 3 times, that's the maximum value that they're talking about here. That would be the 3rd place on my number line if I actually made the number line. So I'm going to add 65.6, the standard deviation right here. Add this 3 times. So if I made a number line and went out to the 3rd place, it would be this 451.9. 451.9, that's what they're talking about here. That's the maximum spot within 3 standard deviations. The minimum spot within 3 standard deviations is when you take the mean of 255.1 and subtract the standard deviation 3 times. And I would have made a number line if the part A had not said within 3. If they would have said between this and that, then I would have made a number line. But since they made part A easier on me, I didn't even take the time to make the number line. So 58.3, if I made a number line, that would be the -3 location. Then 58.3 is the -3. And the 451.9, that's the +3 spot. So basically, Chebyshev's works exactly like empirical rule. You do it exactly the same way. The only difference is the percentages are different. Okay, that's as far as section 3.2 was supposed to go. And we were supposed to do 3.1 on Thursday of the end of the third week, and then 3.2 was scheduled for Monday of the start of the fourth week. And then we do 3.3 on Tuesday of the fourth week. And then there's a quiz over chapter 3 on Wednesday of the fourth week. And then the test is the week after that. Okay, so let me, since I'm at a good stopping point here, let me give you the magic word of this chapter. The chapter 3 magic word, and if you remember the first two magic words, you might guess what I'm going to say next, but I'm going to flip it up on you a little bit. And I can't remember if I mentioned this already in the first half of the video, so let me just do it again in case I didn't. But take the first chapter magic word, the second one, and then you might think where the third one's going, but the third one I'm going to go all the way out to El Paso. So the magic word of chapter 3 is El Paso. Okay, here comes z-scores again. So we're now in section 3.3, but we're still dealing with z-scores. You can, if you make a number line like I did on number 9, the z-scores are just how many places from the mean you are. But you don't have to land exactly at 1 or exactly at 2 or at exactly at 3. You could actually be in between. In the empirical rule, you can only do the ones that are exactly 1, 2, and 3, or -1, -2, and -3. But in general, a z-score, you can just calculate it. It can be any decimal amount even. A z-score is when you take whatever value that you're counting or measuring, some kind of count or measurement, like a test score, for example, or somebody's height. And if you subtract the mean and divide by the standard deviation, this tells you how many places away from the middle you are. So on number 11, they took the tallest living man at one time had a height of 225 centimeters. He was like 8 feet tall or something like that. And the shortest living man at that time had a height of 137 centimeters. So what are their z-scores? And by looking at the z-scores, especially when you calculate more than one of them, you can tell who's more extreme. That they let you compare things that are in different scales. So the average height of men at the time was 172.26. The standard deviation was 5.63. As usual, they have to tell you those two. So take the tall man, take his 225 value, subtract the 172 mean, and divide by the 5.63 standard deviation. So the tallest man was 225 centimeters. Divided by, subtract the mean, 172.26, press equals. Now divide by the 5.63. Now, z-scores usually run between 3 and -3. 99.7% of us land within -3 to 3. This guy's so tall, he's going to be well over 3. He's got a 9.367 z-score. That's extremely crazy to go way past 3 like that. 9.37 if we round to 2 decimal places. 9.37. That's way off the number line, way off the chart. The shortest man was 137.3. 137.3. Subtract the mean of 172.26. This is going to be negative because the person's obviously below the mean if they're the shortest person in the world. And then divide by 5.63. This person has a negative 6.21. Negative 6.21. Oops. 6.21. So the more positive you are versus the more negative, that's who's more extreme. The 9 is more extreme than the -6 because they're basically talking about the absolute value of it. So to be 9 for a z-score, you're 9 standard deviations above the mean, where the -6, you're 6 standard deviations below the mean. So the tallest man was significantly taller than average than the shortest man was by being shorter than average. The tallest man was more extreme. That's what z-scores allow us to compare. Where they're really good is when you do like SAT scores versus ACT. Because SAT, you get like a 1200, and ACT, you get like a 27. So it's just not a fair comparison to say that a 1200 is automatically better than a 27 when they're graded on different scales. So if you do z-scores and maybe the SAT z-score is 1.37 and maybe the ACT is 2.58, well, 2.5 is better than 1.2, so then you'd say the ACT is relatively better. Okay, the next thing we can do is what's called a percentile. Over here. So the z-scores, that's what you do for z-scores. There it goes. Okay, percentile. Percentile tells you how many people you are, what percentage of people you are at or above. So if you take an SAT or an ACT and you get the results back, they'll tell you the national average and the national standard deviation. They'll tell you what your score is, and then they give you a percentile percentage. They might say you're at the 80th percentile. So that means you're at or above 80% of the test takers. And that also means that 20% are above you. So the bigger the number, the better. So you take how many scores are below you, number below you, how many people or objects did worse than you. I don't know if they're doing it here, but often they'll add a half to include ties. And then you divide by the sample size n and multiply it by 100 to turn it into a percentage. So somebody got a score of 1.47, or maybe it's not even people, but 50 different cell phones. So the sample size is clearly 50. Somebody got a 1.47, or some phone got a 1.47. Click this icon to see all the radiation levels. And luckily, these are in order already. So here's the 1.47 way at the bottom. There's only 2 that are higher than that. So this is going to be a very high percentile rank, like 90-some% or more. So how many are below this one? 1, 2, 3, 4, 5, 6, 7, and there's apparently 10 in a row. So 10, 20, 30, 47. There's 47 below this one. 47 below. There's 47 phones below the one we care about. We'll add a half just for kind of like the tie. If there was another one tied with us, then that's where it would be 1, but so that's why it's a half. And then you divide by 50 because there were 50 phones in the sample and multiply by 100. So 47.5 divided by the 50 sample size and then multiply by 100 to turn it into a percentage. This is the 95th percentile. This phone has more radiation than 95% of the phones. So I guess the point is, if you're worried about your phone giving you cancer or something like that, it has a lot of radiation coming off of it. So maybe don't keep it in your pocket, because 95% of phones have less radiation than this one does. So round to the nearest whole number, 95. Okay, so see, sometimes they add a half. Apparently this one's not doing the adding a half. I've seen that in other books where they add a half for the ties, but since there was none tied, maybe this book's not doing that. So let's get rid of the half then and go back and just do 47. There were 47 scores below that one if I don't add the half. And then divide by 50 and now multiply by 100, so 94 instead of 95. And that was enough for them to count this wrong. You'll see it, especially in statistics. I've taught this a long time, and I've used so many different books over the years, and every book has its own little procedures on how they do certain things and different rules on things. There's not a great consensus all the time in statistics. It's one of the newer math subjects too. And it's not like algebra where x equals 3 and you can't really argue about it. Some books just do things a little differently. So yeah, then that's something you just have to know how they want it done here. So apparently they don't want you to add the half. Don't add the half. Just count how many are below and then divide by the sample size and multiply by 100. Okay, the next thing, so let me correct this right here. Take this half off of it. So this should have been 94th percentile, not 95th. Okay, there's something called the 5-number summary. And this is a way to take a data set and show from 5 key spots all over the whole range of the numbers. So we do the minimum value, which is the smallest one. And I'll explain this in a second, but the next one's called Q1. Then there's the median. Then Q3. And the maximum. The min and max, when the numbers are in order, are very easy. These numbers, luckily, are in order. The minimum value is 1, and the maximum value is 6.5. There's 2 very easy answers once the numbers are in order. If they weren't in order, I would take the time to sort them in order first. The computer freezes up sometimes, and it won't write properly. 1.0 and 6.5. Okay, then the median's also easy. That's taught as low as junior high. So let's see how many numbers are here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There's 20 numbers here. So 10 and 10. There's 10 small ones and 10 big ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right there, that's where I would draw the line after the 10th one. So there's 2 numbers in the middle if I was finding the median. And the average of 3 and 3 is 3, so the median is 3. And you could add them up and divide by 2 if you didn't know that, but 3.0. If I do 3 plus 3 and divide by 2, it's still 3. So anytime you average 2 numbers and they're both the same, then the average is the same as the 2 numbers. So min and max, extremely easy. Median's not hard at all. That's junior high work. You just don't know what Q1 and Q3 are yet. Q1's called the first or the lower quartile. Quartile. See, it's like the 25th percentile is what it actually is. The third or upper quartile is the 75th percentile. And what they really are, these are easier to do than those percentile ranks because you don't really need a formula for them. It's just the median of each half of the data. So take the first 10 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right there. Draw a line right there. And don't even look at the upper numbers. Cover up all the upper numbers. Just look at these 10 smaller numbers. If the 10 smallest numbers was your entire data set, what would the median of them be? That's Q1, the median of the lower half. So get rid of the 2 highest and lowest, and the next 2 highest and lowest, the next, and keep going until you get 1 or 2 in the middle. There's 2 in the middle right here, but they're both 2s. So the lower quartile is 2. And then same thing for the upper. The upper is just the average, not the average, the median of the 10 highest numbers. So I drew my line right here. Just look at these 10 highest numbers. Get rid of the lowest and highest, next lowest and highest, next, and there'll either be 1 or 2 in the middle. Here there's 2 in the middle. If there's only 1 in the middle, that's it, but there's 2, but they're both 5, so then the median of that is 5. The upper quartile is 5. So it's 1, 2, 3, 5, and 6.5. 1, 2, 3, 5, and 6.5. That's the 5-number summary. And it's used to make something called a box plot. So I think that's what part 2 is going to be, is a box plot. Yes. So in a box plot, it's basically a picture of these 5 numbers. And you got a line segment going to the left of the box. That's the end of that's the minimum. So since our minimum was 1, the end of that little line, which they sometimes call a whisker, that should be at 1. So that's possible right there. It's also possible here. C is definitely out already because they have the line all the way down at 0. And D basically doesn't even have a line there, so that one's out too. This has got to be graph A or B. And it's definitely B because the Q1, the lower quartile, was at 2, and that's the edge of the box. The edge of the box on the left side is the lower quartile. Here they have the edge of the box about 1.5. The median was 3, so you draw a vertical line in the middle of the box for the median, 3. The upper quartile was 5. See, that's the right side of the box. And then the maximum values where this line goes, which was 6.5. So graph B definitely has the correct box plot. So a box plot shows you a picture of the 5-number summary, and it's also good because it can show us a lot of things. It can show us where the center of data is, like we learned in section 3.1, mean, median, and mode are the center of the data. The line in the middle of the box is the center of the data. It can show you the spread, like the range of the data. How far does it spread out? It can show you the shape. Is it symmetrical or skewed? So, and if there's outliers, they can even do those sometimes. Okay, same deal here, except this problem is mixed up. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Good. So this is different than the previous one. And the numbers are not in order, so I have to do that myself first. There's 11 numbers this time instead of 20. That's nice to have an odd amount instead of an even amount. So let's put these in order. 0.6s, 5s. There's 3 0.5 numbers, 57, 58, and 59. 0.57, 0.58, 0.59. Now do the 0.60s. There's a 0.63, 65, those two. 0.63, 0.65. Goes again, 63, 65. Any 0.70s? Yes, 72. 0.72. Now there's 11 numbers. So I've already reached 5 of them. There's half of them. 0.72 is the 6th number. And now there's going to be 5 more after that. 0.80s. There's 82 and 87. Three more to go. 1.25, 1.47, and 1.13. All the rest are over 1, so 1.13, 1.25. And then 1 point, whatever the last one is, 1.47. So once a number's in order, the lowest number is easy, minimum. Highest number is easy, maximum. This time there's exactly one number in the middle, so that's the median. I don't have to average it. It's just sitting there in the middle. Now, we never use the median to find quartiles. So say you have 1, 2, 3, 4, 5, 6, and there's an even amount of numbers. Then you draw the line down the middle, and the median would be 3.5 because that would be the average of 3 and 4. But we don't use 3.5 to find the quartiles. It's not even one of the original numbers. So then you'd look at the lower half of the numbers only. The middle of the lower half is this 2. That would be Q1. The middle of the upper half is 5. That would be Q3. But if I have 1, 2, 3, 4, 5, 6, 7, now with 7 numbers, there is exactly one number in the middle. That's the median. And then you draw a line on each side of it and don't use it. So the middle of the lower half now is still 2, and the upper half median is 6. But let's say you had 9 numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now 5 would be the median, and you would not use that. But the middle of the lower half of the data is the average of 2 and 3. So sometimes you have to do an average of 2 numbers for the overall median in the middle. Sometimes you have to do an average of 2 numbers to find the quartiles too. So Q1 would actually be 2.5 in an example like this. And Q3 would be the average of 7 and 8, which is 7.5. So that's the situation I have, is there's this one number in the middle. That's clearly the median, but then I don't use that one. So 1, 2, 3, 4, 5. There is exactly one in the middle here. 5.9 is Q1. And 1, 2, 3, 4, 5. The third one there would be Q3. So Q1, let me fill all the answers in. The minimum value is 0.57. Q1, the lower quartile, which is the middle of the lower half of the data, would be 0.59. The overall median was that exactly one sitting in the middle, 0.72. The upper was the 1.13, which was sitting in the middle of the 5 upper numbers, 1.13. And the maximum is 1.47. There's the 5-number summary. Okay, let's make a box plot out of that. So I need to have a minimum of 5.7. The little line segment to the left called the whisker should go down to 0.57. And the left edge of the box should be at 0.59. So if there isn't even a line, maybe that line is coming out a little. It's hard to tell. I guess that is coming out. So those ones are a little harder to tell. Let's maybe look for this 1.47 first. So the right side of the box, there should be a line coming out almost out to 1.5, okay? Yeah, that's okay. That one seems okay, and I guess all 4 of those were the same. So then what about the upper quartile, this 1.13? That's where the right side of the box should be, 1.13. So A is definitely wrong because this is 1. This must be 1.1, 1.2, 1.3, 1.4, 1.5. 1.13 would be about right there. So A is wrong. The box should have ended right there. So 1.13, that could be 1.13. So could that, and that one looks a little bit closer to 1.2 actually. So these ones are hard to tell because the numbers in the bottom here aren't marked, and we got such weird decimal answers too. But I think for sure, graph A is way too far over, and I think C is too far over also. So next I would check the median. The median's 0.72. Here's 0.5, 0.6, 0.7. So now B's out. That's not 0.72 for the median. 0.5, 0.6, 0.7. Yeah, see, that's a little past 0.7. So that it could be D. And I think I've eliminated the other 3, so that would be D. Okay, final problem. Looks like same thing, or did they do this 5-number summary for me? No, okay. Well, I see what's going on here. We got 2 at the same time. We got men versus women, and it's all mixed up. That's not good. What do they want me to do first? The men, probably? Determine the box plot that represents the men, okay? Identify outliers. Okay, this is a good problem in theory, but unfortunately it's going to take a long time with all these numbers here. Okay, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10, 20, 30, 40 numbers, and they're not in order. Dang, okay. Nope, that won't help. Okay, so, well, maybe one thing. I'm seeing a 103 right here. So do any of the graphs don't even go to 103 at the farthest to the right? See, 103, this seems to go too far to the right. That's past 105, apparently. And this could be 103. That could be 103. And then this is when there's an outlier, they put it as an X. So if I could determine whether 103 is an outlier, then I could definitely tell that this is graph D and not graph B or C. What about the minimum? What was the minimum value? 59, 56, 54, 50, 46. So 46 is the minimum. So we've already eliminated graph A. The maximum went too high. 46, this graph B's out now because 46 is down here and it didn't even get an outlier down there. That could be 46, and that could be 46. So at least I'm down to either C or D, and really these 2 graphs are probably the same except, well, I guess the median's different too. So this median's almost at 70, where this one seems to be about 65. And then what about the outlier too, if we could tell if there's an outlier? The problem is I would have to put all these numbers in order, all 40 of them in order, and then figure out all the answers to it. So I guess there's no short way to do that. Okay. So how many numbers are 60s or below? Let me try that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. That's way past 20. Okay. So I was trying to get the 20 smallest numbers if I could find the median quickly. Well, the median's definitely in the 60s then. So it shouldn't go out to 70. So I think graph C is wrong because that median's too close to 70. And there's well more than 20 numbers that are 60s and below. So I'm guessing the median would be this 65 then. And then apparently 103 might be an outlier. So let's try that. Graph D. Okay, so I kind of did that one by process elimination. And I guess you could... you can definitely do this by hand by putting all these numbers in order. I just didn't want to spend 30 minutes doing one problem. So apparently, well, we can look at the graph now. The graph will tell me, see, if there was just a 1x right there, that would be one outlier on the low side and none on the upper side. Or maybe you have two lower outliers. Or maybe there's no outliers at all like graph C. But since the graph was D, they're showing 1x, so that means 103 is an outlier, and apparently it's only 103. Since the graph would have x's in other spots if there were more than one outlier. So at least you can kind of get away on this last problem by just process elimination, figuring out where things should be. So now let's go to the women. There's a tie. No, they have a 103 highest number too. I thought 100 was going to be the highest, but there's a 103 high number. Any of the graphs not have that? This X looks like it could be at 103 because they're saying there's an outlier at 103. This line could be 103. 103, and yeah, it looks like they're all 103, so that doesn't help. What's the minimum value? Anything in the 40s? No. 50. 58. Yeah, there's just that 158. Nothing else is even in the 50s. 58. See, graph C is wrong because that X is too close to 50. The smallest number is 58. That could be 58, I guess. And see, this X could be at 58. They're saying 58 and 60-something are outliers. And this X is way too low. That's almost at 50. So it's either graph B or D. They both at least go down to 58. So what's the next smallest number besides 58 for the women? How many low 60s are there, if any? 61, 63. Okay, so if 58 and 61 were outliers, there shouldn't be another number really close with 63. That's too close to make 58 and 61 outliers. So I would guess that this graph is wrong by having two outliers here at 58 and 61. Then 63 is just too close to that. So apparently there's no outliers on that side. So I'll guess graph D. I already know it's not A and C. Okay. And then I can see now that I know the graph is D, then apparently there's just this one outlier at 103, although that seems to be pretty close to it. But they clearly have it marked as only 103. Okay. So yeah, otherwise your only other option is to write every problem down in order and then figure out the 5-number summary. And that would be a way to make sure you get those graphs right, but that would take an extremely long time, unfortunately. But here's why this problem's important, actually, is once you've drawn both box plots, then you can compare them. You can compare their ranges. How far do they spread out? The men are a little more spread out because their low number goes into the 40s. And both of them have a high of 103. Both the men and women have a high of 103, but the men go into the 40s and the women go into the 50s only. So the men are about 10 more units spread out in their range. So the men are definitely more spread out in whatever this is measuring. We could say they both have one outlier at 103, so that's something they have in common. They might have similar different medians. The median here is like around 75-ish. And this other one was about 65-ish. So the women have a higher average or higher center. And then the shape is determined by coming from the median. If it's significantly longer one way than the other, then it's skewed that way. And usually if there's an outlier on one side and not the other, it's skewed that way. So the men are skewed a little bit to the right since that outlier is over to the right. And the women, their outlier isn't too far out, so maybe this is approximately symmetric. So that's what you'd use it for. I don't know if that's what they're talking about here. It appears the men have higher pulse rates than women. No, definitely not. The women are higher because the women's median is much higher than the men. And so if we don't have the average here, we could use median to tell that. So men have a lower pulse rate than women. It must be C or D. The variation among the men is greater. See, that's what's true. See, it's C here. The men have a lower pulse rate because their median is lower, but they have a higher variation because they're spread out more. And that's what you can tell by looking at the two box plots. So that's where this is useful. Whoops, I guess I messed that up. Let me go back and look at that. The men's median is 65 and the women's is 75. So the women are higher and the men are spread out more. That's weird. From the 40s to 103, while the women are only the 50s to 103. Unless they're using the box. Maybe sometimes they use the box for that. The men's box goes from 60 all the way to about 75. That's 15. The women's box is a little more compact. The box represents the middle 50% of the data. So I guess in general, if the men are more spread out just on their range, maybe it's just one person that's causing that. But since they have a bigger box, then that could say that they are not greater. But this says that they're similar. The variation is greater. Okay, so 40. See, the majority of the men are from 60 to 75. So that means this 65 median is where they sort of are the centered at. Where women go from 70 to about 85. And they're centered at 75. So that's about a 15 spread. And this one's about a 15 spread. So that's where they're saying the word similar. Because the boxes are about the same width. So that's where most of the variation is going to happen. But I would still say the men have lower pulse rates because their median is lower. So let's see if it's this one. Yeah, okay. So what I was doing wrong was I was looking at the overall range from the lowest edge of the whole graph up to the highest. And the men definitely have a larger range. But range is kind of a weak measure of variation because it's only based on the highest and the lowest. Whereas the box itself tells you about the 50%, the middle 50% of the data. So that just gives you a better idea where more people are. So both of their boxes had a width of about 15. So that's why they're saying their variation's similar. This goes from 60 to 75, and this box goes from 70 to about 85. So at least that's the similar part they're talking about. Okay, so now I got 100% on chapter 3, and now you should be able to do any problem in chapter 3.